And we have made it to the end of the end. The final review video for this final exam. Now this one's all about optics, or the study of light. Light is an electromagnetic wave, which means it is a mutually propagating electric field and magnetic field. It does not need a medium to travel through, thanks to research by my boy James Clerk Maxwell. Now, visible light is just part of a wider electromagnetic spectrum. In fact, visible light is the tiniest little sliver of it. It includes stuff like radio waves and microwaves and infrared and visible light and ultraviolet and X-rays and gamma rays, all that kind of good stuff. It all fits into one spectrum. It's all the same thing, just differing wavelengths and frequencies. Now, different materials have different indices of refraction. Now, the index of refraction, all it is a difference in how fast the electromagnetic wave travels through it. So, in a vacuum, or pretty much air, light travels at 3 × 10⁸ meters per second. And this is, as far as we know, according to general relativity, special relativity, the cosmic speed limit. Nothing can ever go faster than this. When it goes through different materials, light might actually travel a bit more slowly. The index of refraction is simply the ratio between the speed of light in a vacuum and the speed of light in that material. The index of refraction can also be used to figure out how much light is going to bend as it passes from one material to another. This is called Snell's law. It's just n1 sine theta 1 equals n2 sine theta 2, where n1 is the index of refraction of the first material, theta 1 is the angle of incidence. Now, theta 1 is not the angle from the surface to the light ray. Oh, no, no, no. Theta 1 is the angle from the perpendicular, an imaginary perpendicular line to the surface, to the light ray. Same deal with theta 2. Once it's passed into the second material, theta 2 is just the angle from the perpendicular to the surface inside the material to the light ray once it passes through. So, the higher index of refraction, the lower the angle will be for you. And the lower the index of refraction, the higher the angle, according to Snell's law. You'll need to know about total internal reflection as well. This is a special case of Snell's law where you start from a higher index and are heading toward a lower index. Ordinarily, it would just refract out like normal, but if you pull theta 1 up enough, eventually you'll get theta 2 to be exactly 90 degrees, meaning that light ray is just skimming the surface and not actually leaving. Any angle higher than this, there won't be any refraction because Snell's law breaks down, and you end up with just reflection back into it. Total internal reflection. So you can find the critical angle, basically is just the inverse sine, or the arc sine, of n2 over n1, where n2 is the second material, the smaller index of refraction. You need to know about lenses, too. The thin lens equation is simply 1 over the object's distance, and notice this is the distance from the lens. All of this is relative to the lens. So the object's distance, 1 over the object's distance, plus 1 over the image distance, again, how far the image is from the lens, equals 1 over the focal length. As lenses are crafted, they've got different focal lengths, and generally that'll be given to you. You'll also need to know the ray diagram for a thin converging lens, particularly just these 3 principal rays. When you draw your thin converging lens, you've got what's called the principal axis. It passes right through the center of the lens, perpendicular to its surface. Meanwhile, you've got an object, let's say its base is right on the principal axis, and it has a certain height. From the tip of that arrow up at the very top, you will have one ray that comes off the arrow, hits the lens, and refracts and passes through the focal point. So F is the focal distance, the focus, away from the lens. This I'll go ahead and call SO, that's the distance of the object, and SI is the distance of the image. All right, so the first ray comes off parallel to the principal axis, strikes, goes through the focal point, and down. The second ray does the exact opposite. It starts by going through the focal point on the other side first, hitting the lens, and coming out parallel to the principal axis. So parallel to focus, focus to parallel, and finally you've got the last ray that comes down, and it strikes the lens at the middle and just continues on through. Where those three lines intersect, you get your image. If your image is upside down, it is said to have a negative height. Speaking of heights, you can find it using the thin lens magnification. If HO is the height of the object, which will simply be the length of the object from the principal axis up to its highest point, that'll be HO, and HI will be the height of the image, then the magnification, which is just a unitless quantity, will be HI over HO, also known as negative SI over SO, meaning negative image distance over object distance. So, for the example of a thin converging lens, which is really all that we had time to get to, it produced an upside-down inverted image. So HI is negative, the magnification is also negative. The magnification can be bigger than 1 if the image is taller. It can be smaller than 1 if the image is shorter. And that about wraps it up. Whew. Jot down any questions you may have. Bring it into class next week. We will meet Monday. We will meet Wednesday. And then you will take your exam on Thursday. Those of you who have AP English, I believe, and there might even be 30 some of you, I don't think you'll be there Wednesday. So be sure you bring any questions you may have on Monday, as that'll be your last class meeting with me. All right. See you next week. Have a great weekend.